vibration is done, we are now going to go to rotation. Again, what the game we play? We have a diatomics which is rotating, and then we go and calculate the solve the Schrodinger equation assuming as a rigid rotator. Remember rigid rotator of quantum mechanics? Okay. And what are the energy levels? Important thing is that I is moment of inertia in the denominator, just like in translation m would be in the denominator. So, moment of inertia more, energy levels get quashed together. Okay. So, this is the we usually use this notation, but I do not see where I use this one. So, Ej. So, now important thing, one very important thing in a rigid rotator, that given J is the quantum number, like N there was the quantum number in harmonic oscillator, J is the quantum number. However, here it comes with a degeneracy. If you remember, rotational levels come with a degeneracy. Anybody remembers? Raise hand. Who remembers the rotation has a degeneracy? Okay, one guy remember, two guys remember. These two doesn't, and rest, or you three remember, others don't. That so, and when there is a degeneracy, then it is trivially, partition function is written trivially so this factor is the degeneracy factor, degeneracy of an energy level okay. So, it is just the weight, G is the universally used as a weight factor, it is the density of states, G is used as a density of states, and so it is essentially weight of that, like in radial distribution function again G used. So, G comes, we use G as a is almost universal thing in a density of states, and so this is the same thing. So, this is the density of states 2J plus 1. So, I put it there, and this is the energy. So, I put the energy h square j plus 1. Now, something very interesting here, did you notice that? That if I take derivative of that, I get that quantity. This is one beauty. So, then I write this quantity, but if I take the derivative of that, what happened? J square plus 1 become 2j plus 1, but I also get out h square by 8 pi I square I k t, which I should then compensate for, and that is compensated here. Okay. So, now write the partition function in a very neat way in the following form. It is pretty neat, very nice, but unfortunately we cannot evaluate it. Nobody has been able to evaluate this. So, our rotational partition function remains a little bit stuck. This has to, but of course these days is trivial. Before people used to have tables, and people tabulated tables for all rotation and different molecules. Our times we used to have tables, but now you do not need tables, tables have disappeared because you can put in one line in computer. So, you see now in this case there is a very strong dependence on moment of inertia I, okay, very strong dependent on moment of inertia I in the, it's very, as I told you, it's very important. So, low temperature, but we can, though we cannot evaluate this one, we can evaluate high and low temperature, because at low temperature there is one case, high temperature one case. A high temperature this becomes small, low temperature this becomes very low temperature, this becomes so large, this becomes large, and to negative it goes to 0. So, low temperature only first term would be enough, okay. So, and then low temperature I can just evaluate this, j equal to 1 becomes 1, j equal to 0 become 1, then I need to keep only one term, j equal to 1, that is 3, okay, and then I get this term, and that is pretty good, okay. So, this is the partition function at low temperature. High temperature, now gap between energy levels become very small. So, I can now replace this sum by an integral, okay. Is that clear? When things become very close, it's like translational partition function. I can replace the by an integration, and this integration I can evaluate, Anyway, I know that this is d by dj, and d by dj is trivial to integrate because you just evaluate in the two limits, because integration is done for you, and then that is this quantity. So, in the high temperature, your rotational partition function is T 8 pi square I by kBt. Now we define, since this quantity has a dimension 1 over temperature, then I define this temperature as a rotational temperature. These things are important because this can tells you that what is the relative rotational temperature, tells you below this temperature you have to be a low temperature limit, above the temperature you have to treat it as high temperature. Similarly, in vibration, theta vibration tells you there is a crossover temperature. Below that and above that, things start changing. Of course, it does not change at that temperature, but it kind of goes through this swing. So, it gives a very good estimate of doing those quantities. Now, we go again and do the partition function minus kBt ln q. Again, I have a bunch of rotators which are non-interacting. I have n kBt ln q rotation. Now, this q rotation is ln 8 pi square by a kBt. This is I am doing now the high temperature, and as I told you, many of the cases high temperature is reasonably okay because it is 80 centimeter inverse. You are drawing say 300 Kelvin to 1 centimeter, you are not greatly, but still you can get away. You are better than low temperature limit, and then that is this quantity n comes out because q is q rotation to the power n, that comes out minus n kBt ln 8 pi square I kBt by a square, and then I use my theta r again. So, I have this neat expression of free energy n kBt ln T by theta r. Okay, remember that. Now, I play the game again. I find what is the rotational entropy. That is a term turned out to be extremely important in modern days. What is the rotational entropy? It was not, in our time when we studied these things, we really thought Sackur-Tetrode equation, translational partition function only good for PV equal to kBt, the beautiful derivation. Then vibration, we liked it very much. We knew because side by side solid-state physics or solid-state chemistry was taught, so we knew that. Rotation we did not pay any attention to. However, it turns out I will tell you why it is so important. So, this is the entropy. Now, I take this derivative from here, this quantity, neat and clean and very simple. So, I can calculate the rotational entropy, right. We go there, you take the derivative, one term comes from here, another term comes from here, and when I do that, I get this is the first term, this is the second term. So, this is the beautiful expression for rotational entropy. Then I take the specificate just like I did in vibration, and then I get derivative of that. This term does not carry exactly parallel to vibration. So, then this ln become 1 over T by theta, then a, and it becomes 1 over T, and that cancels, the T cancels the 1 over T, minus minus, and all these things will become nkb. Okay. So, rotation, so the beauty is that rotational specific is nkb, vibration you already know. So, it becomes R. Okay. Now, we will just talk of some of the thermodynamics. So, we have now derived all the things, vibration, translation I did in the morning, we did vibration and rotation, and I have to come back and do little bit of monatomic, but that I will do a little later because there is still some amount of way to go. And as I told you that I wanted to start fresh and do this good job to diatomics because that is not done in a unified way. I have not seen even all the StatMech books have not done a good job in bringing the whole picture clearly to a. Okay. Now, let us see some examples again. So, ideal we go to now, okay, before we do that, ideal polyatomic molecules, we did ideal monatomic, ideal diatomic and polyatomic. For example, linear you have 3, translation 2, rotation, these are the vibration, these are our standard questions in oral, sometimes even in PhD interview, for, of course, even in your job talk, even in job talk sometime we ask the suddenly the faculty candidate also ask these questions. So, if we are nasty, we ask that, and many times we find that by that time they are giving a job talk, they have forgotten these basic things. Okay. So, you know all of this, na? That in a nonlinear 3 rotational degrees of freedom, so 3 n minus 6. Okay. Vibrational partition function, total partition function, rotation, not vibration, is total partition function then is translation, nonlinear means 3 rotation, then 3 vibration. So, this is the total partition function. This should be total partition function. So, this is the total partition function in all its glory. So, vibrational partition function is this quantity, rotation and translation we just described. The reason of writing it separately, it was not written before. Okay. So, this is the rotational partition function of a spherical top. Spherical top is like methane is, we are now doing polyatomic, we have done monatomic, diatomic, polyatomic, and this is where much of the, well, diatomic already lot of interesting things are there like oxygen, nitrogen, then you have carbon dioxide, not carbon dioxide, carbon monoxide, nitrous oxide, cyanide, all these things are diatomic, but polyatomic is where water, methane, ethane and ammonia, all these things. So, but you have symmetric molecules, then all the moment of inertia are the same. That is the definition of a spherical top. Then it is very easy. This is the thing. These things do not matter in vibration, but it matters in the rotation. Then there we can do these calculations here. Then this integration, as we did just before, is the same thing again done. However, if they are symmetric top, not spherical top, then the condition is that 2 are equal, but third one not equal, moment of inertia. In that case, I write the rotational partition function in the following way, clear? 2 of them, that is why half goes away from here, third one, the asymmetric one comes here as the half. So, this is the partition function of the rotation of asymmetric top molecules, and that can again be calculated by the kind of approximation. Now, if it is completely asymmetric, then you have to work much harder, you have to write IA, IB, IC are completely different from each other, then you have to write them explicitly with their moment of inertia. There is a symmetry number that comes to take care of the symmetry of the Hamiltonian here, which is typically 2 or 3, but I forgot the exact origin of that. And anybody remembers? This is classical mechanics, otherwise we have to clarify in the next lecture. Okay. In terms of theta r, this is the rotational partition function. So, all these things work done now leads to, this is the table that I wanted to talk of, that characteristic temperatures, and then we now beginning to see what is the what is the low temperature, high temperature approximation. Look here, water, so this is with, remember, with respect to kBT, h nu by kBT, and this similarly theta rotation is, here is the theta rotation. So, this is essentially the moment of inertia, everything else is constant. So, then look at here how high these things are in vibration. Rotation, they have come down drastically. Water is an, there is no symmetry, and all the 3 vibrations are different, all the 3 rotations are different, IA, IB, IC, 2 of them are close to each other in vibration, but rotation all 3 are different. Here is ammonia, and these are the ammonia vibrations, and these are the rotations of vibration, then sulfur dioxide, all these things. Now, these are given in my book, and they have been one of the important things, that say all these things are taken from the book. Now, this is entropy of polyatomic molecules. So, this is trivial because they are not interacting. So, entropy is the sum of the entropy. So, you have the rotation, this is the translational entropy, Sackur-Tetrode equation. This is the vibrational entropy in the general form for anisotropic molecules, and this is the vibrational entropy. So, translation, rotation, vibration, 3 things added. Now most of the time, because of vibration, water, this is so high that there is only one term that is important. And here is the table for water, and translation is, this is the absolute value of entropy, that it is 17. But look at rotation, rotation is 5.45. That is, rotational entropy is about 30% of translation entropy. This is an extremely important result. For ammonia is again, but look at vibration, vibration entropy is negligible. So, if I think of water, ideal entropy of water, which I told you is a significant, actually real entropy of water, still these 22 makes a huge contribution. Entropy goes down to maybe a value of 10 or 12, but this still makes the lines contribution. So thermodynamic properties of water and ammonia, lines contribution comes from the ideal. This is something I had no idea myself when I was taken away completely by this interaction and all these things. But ideal plays a very, very important role. So again repeat, then in case of water, rotation, vibrational entropy makes no contribution. Rotational entropy is about 30% of total, and this is the decomposition. But you can see, though these are fairly different molecules, there is a near constancy of, yes.
That is because this entire development is purely geometry. There is nothing about the chemistry of the molecules.
That's correct. Yeah, chemistry of the molecules will come through electronics, and so that's a good question. So, but the ammonia and water is different chemically because of their electronic properties. Also, there is a polarizability, which is again electronic properties. And so we are doing idea also, and because of electronic and polarizability and the shape of the molecules, interaction between two water molecules and two ammonia, or between water and ammonia, they are very different. Those things are not here. So we are not having any interactions. So when I am doing of thermodynamic properties, ideal gas, but we should not be carried away, you are right. When it comes to chemical properties, then the electronic features play an important role. Okay. So the translation entropy contributes most, but rotation is 30% of the total. Actually very recently, till about 5 to 10 years ago, when we were calculating entropy of water, we are neglecting rotation contribution. And we are writing a paper which will be submitted in the next few days. I told you that you are doing a ice water interface, and ice water interface, the ice goes into water. In the ice, you either have translation entropy, not of much rotation, but when it goes to liquid, translational entropy you don't gain too much because it's still highly constrained. But rotational entropy is the one that dominates ice water interface. For any molecular solid, rotational entropy is very easy to recover because rotation is not a conserved quantity, but translation is a conserved quantity. It's very important. So I can destroy the rotational order very easily. You know, I can take one out of a rotational degree of freedom, but I cannot do it in real space. Orientation is not a orientational density is not conserved. Conservation is a spatial density or number density. Yeah, but you see, it can be anywhere in the sphere. So again, it's a very fundamental concept coming from a little bit different field, but it is a number density. Okay, if I hate to do that because I think most of you will not be able to follow it, but let me tell you, let me try. I have a density which is space dependent and I have a orientation dependent, okay. I write it as a spherical harmonic expansion. That's what I didn't want to, I should not have said what I said because it's just going to confuse you guys. Now this density is conserved. Where does the conservation come? If I integrate over and I say that's a conserved quantity, that will then, this conservation will be constant only on A00, isotropic part. orientation, this you have to think yourself. I think I should not have got into that, and I don't want to get into that, but that's a very interesting thing. I mentioned in the context of rotational entropy that many cases you recover rotational entropy, but you do not recover translational entropy. Okay. This is the part of I now want to go back and 5 minutes do the okay, these we have done in the morning up to this day. Chemical potential, grand canonical, take the derivative, now we will do what the question you asked, that what is the way to do the microcanonical ensemble for ideal gas, right. And I said the following, it is very difficult in a classical, but it is trivial in quantum. So if I want to do if this is the ideal gas, monatomic ideal gas, this is the Hamiltonian. So partition function should be dr1, I just do one particle, dr3, dp1, dp2, dp3, then delta H minus E. So NVE constant means Hamiltonian has to have constant energy. Okay. So you pick up a hyper surface, and this of course gives me just the volume as before. But this has to have this constraint. So I cannot have any momentum and any A. So you see what it become trivial in the canonical partition function, because I have just have a Gaussian integral, because I allow energy fluctuations in by bringing temperature. But in the constant energy surface, this is you can do only numerically. Okay. However, in quantum it becomes easy, because in quantum I have to sum over energy levels and I can solve particle in a box, and this is my volume here, right, the length of the box. This is a cubic, I can give a cubic box, then it is like that. Okay. Now this is nx, ni, nz, all I introduce as n square, then that n square here, if is the constant, if energy E is there, then I can go, there is a reason I am going to do that. This is very cumbersome way. I will first define the energy, then I will say nx, ny, nz can be 0 to infinity, and then it is amazing that students, even after 5th year PhD students, they have no idea many times how to write equations. Of course, that is the problem we come in chemistry. I remember I worked with a very distinguished physicist who is now a chair professor of some university of Urbana. He has a very famous book on statistical mechanics called Yoshiko Ono. And I used to work with Yoshi at one stage in Chicago when I was a postdoc, and Yoshi always used to tell me, Viman, why do you write equations in such cumbersome form? And a physicist has certain affection and love for mathematical equations, which shows in their writing. Here also see how cumbersomely it is written. Okay, nx, ny, nz are all of them from 1, they are not from 0, remember? Okay, if that is, then if I should introduce that these quantities n squared because they come together, remembering that nx, ny, yz can vary, each of them independently, then I put them equal to E. Now I am going to use something, because these nx, ny, nz make a cubic system. I vary nx along x axis, ny along y and z. They are discrete points in a digit, in a grid. So, however, since mine is 1 to infinity, I populate, because of my energy levels, 1/8 of that. Okay. So, however, the n square I can write as this quantity, a vector in that space is n square, and that is given by E. So, that is this 8 ml square H square by E. Now, in 3 dimensions with the radius n, so I can calculate the density of states by calculating the number of points. Is this clear? So, these are all so my total number now nx, ny, nz are all positive. Okay. So, there will be only one side of that will be I need to calculate. Okay. It is not the whole space. So, if I do that, then it is 1/8 of the whole average. So, total number of points is in the radius is n is nx square, ny square, nz square. This is really lucky. So, then it is 4 pi by 3 pi n cube. This is the volume. So, 1/8 of that n I know because that is connected to energy E. I have a NV ensemble, ideal gas in NVE, they are non-interacting. So, my volume of the box comes through L, energy comes through E, total N will be when I put them to the N because N number of them. So, NVE each plays a role. Okay, it's really very pretty. So, this is your density of total number of states. Omega of that gives you the partition function. Oh, sorry, this is your partition function, ln of that gives you the entropy. So, this is the way, this goes on doing the what solid state physics, the density of states and all these things, but we do not need it right now for statistical mechanics. This is used in some cases, but if we need later we will do, but this is where correspondence between quantum and classical statistical mechanics of a monatomic ideal gas. This is the capital omega, this is total number of states. Capital omega, which depends on, I should have put it into capital omega again. So, this is the depends on E, this is depend on V. Of course, because n can be 1 to infinity. Particle in a box, remember the quantum numbers from 1 to infinity. You remember that or you forgotten? Okay. So, then no, between doing so you are using, so these, that is why many parts of statistical mechanics we cannot teach unless quantum is done. Like we know particle in a box, we need harmonic oscillator, we need rigid rotator. So, that is why in everywhere StatMech 1 starts in the second semester. First semester quantum 1 and thermodynamics. So, courses that I have taught in many places, it was always the second semester, which was very bad because everywhere StatMech used to be full winter. When I taught at Harvard, taught at Wisconsin, everywhere, it was always the month of January, February, March, April, which is horrible. Thermodynamics is the first semester, which is the called fall. Here also, in at our Indian Institute of Science, SS 201, sorry, our solid state, SS 201 used to be thermodynamics, SS 202 used to be statistical mechanics. Same in physics everywhere, but by the time we are doing SS 201, side by side SS 204 or 5 is the quantum mechanics. So, quantum is done parallel to thermodynamics, then comes the statistical mechanics. Okay, but that is a different thing. So, this is what completes, I said I will take 10-15 minutes more, is done. So, next in the book, one usually goes doing Bose-Einstein condensation and Bose statistics. I am not going to do that, that we will do later, because this is a non-interacting system. I think next what we need to do is the interacting system, because that is where much of our applications are. But if you do not do the ideal gas or ideal case, then you cannot do the interacting systems.
Okay, so when you are calculating the translation of partition function for this polyatomic, the masses may be different, right? But in have different masses, what mass you take for the translation?
No, you take the center of mass. Center of mass is always well defined. Yeah, the center of mass, total mass. And then total mass, then for rotation, you will have mass of the, you will have moment of inertia along each axis. There are three principal axes. So, in nonlinear molecules, we have three moment of inertia, I1, I2, I3. Similarly, when you do vibration, each vibration will have an effective mass. So, translation will have one mass, which is the central mass, and then three masses for vibration, three masses moment of inertia for rotation. Anything else? Okay.